Next up is halogenation. Now, halogenation is going to be the addition of just halogens. So here, this will occur in multiple steps via a three-membered ring intermediate, which I will draw for you. Now remember, an intermediate is different than a transition state. A transition state is that transient species. It's a proposed structure that's formed en route. It's something that we propose based on the structure of the reaction and the product. Whereas an intermediate is something that can be observed. And so you'll get to see that. And I'm not going to use those square bracket notation on an intermediate because it's formed, it's stable-ish, and then we continue to do chemistry on it. Now, since we're adding two of the same atom, there is no such thing as Markovnikov or anti-Markovnikov addition, so nothing to worry about. The addition of the two X groups itself is going to be anti, or on the opposite side, remembering that syn meant on the same side. You'll notice here that we've added the two X groups to the two alkene carbon atoms, and the alkene has been transformed into an alkane. Now, keep in mind that the halogens that are most commonly used in this reaction are bromine, which is a liquid, and chlorine, which is a gas, as they are reactive enough to do chemistry, but not so reactive that they lead to undesired side products. Fluorine, F2, is very difficult to do chemistry on, which is why we don't see it in second-year organic chemistry. Iodine is pretty sluggish and unreactive, which is why we're really going to be seeing chlorine and bromine as the #1 examples. Now, these reactions are done in extremely unreactive solvents to avoid side reactions. Now, we saw the consequence of a reactive solvent in acid-catalyzed hydration and hydrohalogenation, where water could be both a solvent and a nucleophile. It's for this reason that we use non-reactive solvents, and the best example here is going to be carbon tetrachloride, which is here, or benzene, C6H6, remembering that benzene looks like this. And in fact, we did a whole section where we saw that benzene was so unreactive that we needed special catalysts to make it do chemistry. So just keep that in mind, that we're going to be working with unreactive solvents in order to prevent side pathways. Now let's look at the mechanism and the formation of this intermediate. So the steps of the halogenation are going to be first nucleophilic and electrophilic attack of the halogen to the alkene. We're going to see how that occurs in just a moment. Followed by nucleophilic attack of the halogen anion onto that three-membered ring, which opens up that three-membered ring to give our final product. So let's take a look at this. Let's deal with this first step first. So we're going to have this Br2, which I'm going to show here as Br. Now, this first step here is pretty unique in that the bromine will be both nucleophilic and electrophilic. Now, it's going to be nucleophilic because it has a lone pair. It's going to be electrophilic because it has a transient dipole, rendering it partially electrophilic. Now, the alkene is also going to be nucleophilic and electrophilic. Remember, nucleophiles and electrophiles are both candidates for an alkene. An alkene can have both behaviors. So we're going to see both species acting as both types of reagent in this reaction. So let's draw it. We're going to have attack of the bromine onto the alkene, and the alkene will also attack the bromine. So you'll notice both species being both nucleophiles and electrophiles. This bromine atom in the Br2 will depart, and this is going to lead to formation of the product. Now I'm going to draw it here for you. Again, we're going to show this methyl group. There's no chemistry happening there, so we don't worry about it. And we're going to form a three-membered intermediate. This three-membered intermediate is going to look like this. The bromine atom, you'll notice, is added to the same side. And you'll notice here that I drew it on the bottom face, but could have drawn it on the top face, and that's important. Here, I'm going to put a positive charge, and I'm going to draw both structures just so you can see them and understand what's occurred. So again, I could show the bromine atom added to the top face as well. Same deal with the charges, methyl groups pointed down. Now, the reason why the bromine atom is added to the same face, why we have both wedges or both dashes, is because of the constraints of the ring. The ring is only 3 members, which means it's really constrained, which means that the bromine has to add all to the top or all to the bottom. Okay, so now we're ready to do the final step, which is to bring in this bromine atom that departed in the first step. And we're going to get a tack of the Br. Now, I'm going to draw a whole bunch of products here, and I'm going to split them up so we can see all of them. Now, you can understand now that the bromine nucleophile can attack either this carbon here or this carbon here. We're going to draw a tack at the green one first. So the bromine will come in and attack and open up this ring like so. And I'm going to draw the product of that reaction. Again, 6-membered ring. This methyl is just hanging out. Now I'm going to have the Br. Now I'm going to have the Br up like this, the methyl pointed down like this, and the other bromine is going to be on the top face like so. And the methyl will be down like so. You'll notice here that the bromine atoms are added on the opposite face of each other because the 3-membered ring was pointed up, and therefore the nucleophile is going to approach from the opposite side. Now let's see attack at the pink carbon. So for the attack at the pink carbon, we're going to do the same thing. We're going to have the Br minus, and we're going to attack here on the opposite face, and this ring will also open up. We're going to get the same sort of product. This methyl group just hanging out. Now the bromine that was down is up here, and the bromine that attacked is over here. And again, the methyls will be here and here. And so you'll notice again that we have the bromines added anti to each other, and that the nucleophilic bromine could attack either carbon atom. And so here we have the 2 potential products where this was the nucleophile at this particular carbon. Now we have to do the same thing to the other structure we drew. So let's take a look now at attacking the green here and pink carbons of the other structure, and then we can compare. So again, mechanistically, it's the same. The bromine nucleophile comes in and attacks, and the ring will open up. This will give me a couple different products. Let's draw the first one here, where we have the bromine up here, the methyl pointed down, this methyl just hanging out, and therefore we have the bromine atom down here and the methyl up. And this comes from attack of this bromine to this green carbon. Now let's draw the product of the other reaction. Again, bromine nucleophile hanging around. We attack, we open, and I am left with these structures here. We will get them all nicely drawn in. The bromine here attacked from the bottom face. We have a methyl, and here on the top, therefore, we have the bromine with the anti-addition and the methyl like so. This is a lot of products, right? And this is why this reaction is more complex than it would appear. So let me recap what has happened here. We have this sort of wild first step where we have both nucleophilic and electrophilic bromine and alkene, which forms this 3-membered ring. Now, our 3-membered ring was pretty complex because there's a stereocenter already built into the molecule, and we have formation of the Br ring above and below the alkene. We then need to think about the regiochemical attack whether or not the bromine attacks the green or the pink carbon with equal preference. And that opens up the ring in two different ways and leads to two different stereochemical outcomes. Both are anti, but we have to pay attention to which is which. We have to do this on both rings and draw all the possible outcomes, where I've highlighted them in green and pink, showing who is nucleophilic and which carbon we've attacked. At that point, you can take a look and you can assess all these different stereochemical products to see if any of them are the same. But it's important to show them all, especially with an example this complex. It is unlikely you will be presented with something this complicated, which is why I'm bringing it to you here so you can see the hardest possible before you have to see slightly easier examples. Now, there's one last consideration in this reaction that I'm going to go through. Now, the last thing to consider is the fact that this chemistry is called stereospecific. What stereospecificity means is that the structure of the reactant dictates the structure of the product. In other words, if there's geometry where I start, that geometry must be maintained. This is best seen with alkenes, where we have stereospecificity in our products. If we have a trans alkene, this must remain trans in the product. If we have a cis alkene, this must remain cis in the product. Let's take a look at how that manifests. If I'm to do bromination of a trans alkene, I should get a product like so, where the methyls will be on opposite sides, like so, and the bromine atoms will also be on opposite sides, like so. This here provides us a structure of anti-addition of the Br2, as well as maintaining the trans configuration of the alkene. Now let's take a look at the cis stereochemistry. Now here, the two alkene methyls should remain on the same side, but the bromination remains anti. Let's see what that looks like. Here, the two methyls will remain on the same side like so, but the bromine addition here will be anti. So just ensure that you're watching out for that, especially for non-ring examples. Remember, stereospecificity says to us that the stereochemistry of the reactant dictates the stereochemistry of the product, which means that cis alkenes remain cis and trans alkenes remain trans. That's halogenation with its weird three-membered ring intermediate. So again, you should be able to predict the product, think about the stereochemistry, and draw that mechanism.